the relationship between A and A. Welcome, everyone. Before we dive into today's new topic, let's take a quick moment to reflect on what we have already covered. In our previous lessons, we worked through the step-by-step process of constructing the adjoint of a square matrix. You should all be familiar with how we first find the cofactor matrix and then transpose it to arrive at the adjoint. Now, building on that foundation, we are moving into something much more powerful. Today, we are going to explore a fundamental property that creates a direct link between three key players in matrix algebra: the square matrix A, its adjoint, which we write as a J, and its determinant, denoted as the absolute value of A. This isn't just an isolated rule to memorize. This relationship is actually a cornerstone of matrix algebra. Understanding how these three elements interact is absolutely essential, as it provides the theoretical groundwork you will need to master the process of finding the inverse of a matrix, which we will discuss in more detail later in this session. Understanding the theorem. This theorem defines a very special relationship. It states that if we have a square matrix, let's call it A, of order n, then when we multiply this matrix A by its adjoint, which we write as a J, the result is something very specific. The product is equal to the determinant of matrix A, multiplied by the identity matrix of that same order. To see this more clearly, let's look at the mathematical notation. We express this relationship as A multiplied by a J equals a J multiplied by A, which both equal the determinant of A, times the identity matrix I. Now that we've recalled how to construct the adjoint matrix from our previous lesson, let's move on to the heart of today's topic, the theorem. As we will see in the next few slides, this isn't just a random formula. It's a fundamental property that tells us exactly how the matrix and its adjoint interact to produce a scaled version of the identity matrix. Breaking down the formula. Now that we have seen the theorem itself on the previous slide, let's take a moment to break down the formula piece by piece so we know exactly what each component represents. First, we have A, which is our original square matrix. Next, we have a J, which stands for the adjoint of matrix A as we discussed in our earlier lessons. This is specifically the transpose of the cofactor matrix. Then, we have the vertical bars surrounding A, which denotes the determinant of matrix A. It is very important to remember that this value is a scalar, meaning it is just a single number, not a matrix. We also have the letter I, which represents the identity matrix. You can think of this as the matrix version of the number 1. It is a square matrix with ones on the principal diagonal and zeros everywhere else. Finally, let's look at the term on the right side of our equation, the determinant of a multiplied by the identity matrix. When we multiply a scalar by the identity matrix, we get a diagonal matrix. In this specific case, every element on that main diagonal will be equal to the determinant of A, while all other elements remain 0. Understanding these individual parts is crucial before we move on to the conceptual explanation of why this mathematical relationship actually works. Conceptual explanation. Now, you might be looking at this theorem and wondering, why does this happen? Why does this specific product result in such a clean, diagonal matrix? To truly grasp the logic, let's look under the hood at what is actually happening during the process of matrix multiplication. Think back to how we calculate a determinant. When we multiply a row from matrix A by the corresponding column from the adjoint of A, and remember, that column is actually a row from our cofactor matrix. We are essentially performing the exact same expansion calculation we used to find the determinant of A. This is why, on the main diagonal, we get the value of the determinant. However, something very interesting happens when we multiply a row of A by a column of the adjoint that does not match that row. In these cases, the calculation effectively cancels itself out, and the result is always 0. Because all these off-diagonal elements become 0, we are left with a diagonal matrix, which is simply the identity matrix scaled by the determinant. This explains why the result looks exactly like the determinant of a multiplied by the identity matrix, which we will see verified in our upcoming step-by-step example. Step-by-step example. Now that we have understood the theory and the conceptual logic behind why this relationship exists, let's put it into practice. To verify this theorem, we are going to work through a concrete, step-by-step example. We will start with a simple 2x2 matrix, which we will call matrix A, where the first row contains the elements 2 and 3, and the second row contains the elements 1 and 4. Step-by-step example, continued. First, we need to complete step 1, which is to calculate the determinant of A, denoted as the absolute value of A. To find this for our 2x2 matrix, we multiply the elements on the main diagonal, that is, 2 times 4, and then subtract the product of the off-diagonal elements, which is 3 times 1. This gives us 8 minus 3, resulting in a determinant of 5. Next, we move to step 2, where we find the adjoint of A. Written as A, since we are working with a 2x2 matrix, there is a very handy shortcut you can use. Simply interchange the elements on the main diagonal and change the signs of the off-diagonal elements. So, our 2 and 4 swap places, and our 3 and 1 become -3 and -1. This gives us our adjoint matrix, which has 4 and -3 in the first row, and -1 and 2 in the second row. Now that we have our matrix A, let's move into the actual calculations to verify the theorem. Keep these values handy, because in the next slide, we are going to multiply our original matrix by this adjoint to see if the theorem holds true. Step-by-step example, continued. Now that we have our original matrix A and we've found the adjoint, let's move on to step 3, where we actually calculate the product of A and its adjoint. Looking at the screen, we are multiplying our matrix A, which has 2 in the first row and 1 in the second, with our adjoint matrix. To do this, we perform standard matrix multiplication, working through each element one by one. First, let's find the element for the first row, first column. We take the first row of A and multiply it by the first column of the adjoint, 2 times 4 plus 3 times -1. That gives us 8 minus 3, which equals 5. Next, for the first row, second column, we multiply the first row of A by the second column of the adjoint, 2 times -3 plus 3 times 2. This results in -6 plus 6, which simplifies to 0. Moving down to the second row, let's calculate the first column. We take the second row of A and multiply it by the first column of the adjoint, 1 times 4 plus 4 times -1. That gives us 4 minus 4, which is also 0. Finally, for the second row, second column, we multiply the second row of A by the second column of the adjoint, 1 times -3 plus 4 times 2. This gives us -3 plus 8, resulting in 5. As you can see, our resulting matrix has 5s on the main diagonal and 0s everywhere else. In the next slide, we will compare this result to our determinant to see if the theorem holds true. Step-by-step example, conclusion. Now, let's look at the results of our multiplication from the previous step. As we just calculated, the product of matrix A and its adjoint, A, results in a new matrix where the top left element is 5, the top right is 0, the bottom left is 0, and the bottom right is 5. This brings us to step 4, where we perform the comparison. To see if our theorem holds true, we need to calculate the right side of our formula, which is the determinant of a multiplied by the identity matrix. Recall from our earlier steps that the determinant of A, or a vertical bar, is equal to 5. We also know that the identity matrix, I, is a standard 2x2 matrix with 1s on the main diagonal and 0s elsewhere. When we multiply this scalar value of 5 by the identity matrix, we distribute the 5 to every element inside the matrix. This gives us a new matrix where the diagonal elements are 5 and the off-diagonal elements remain 0. So, looking at both sides, we can reach our conclusion. Since our calculated product, A, is exactly the same as our calculated value for the determinant of A times the identity matrix, both resulting in a matrix with 5s on the diagonal and 0s elsewhere, we have successfully verified the theorem. We have proven that A equals the determinant of A times the identity matrix. This confirms that the mathematical relationship we discussed at the beginning of this lesson is indeed correct. Real-world analogy. Imagine you are working with a scaling filter in digital image processing. Think of the original matrix, A, as a transformation applied to an image, for instance, something that stretches or distorts the pixels. Now, think of the adjoint of A, or A, as a sort of pre-correction mechanism. When we multiply these two together, as we saw in our calculation, they don't perfectly cancel each other out to return us to the exact original image. Instead, they return us to the original state, but with a twist. The image is scaled by a factor of the determinant of A. In this analogy, the identity matrix, I, represents that original, untouched state of the image. The determinant, which we call A with vertical bars, acts as the scaling factor that grows or shrinks the image. So, the equation we've been studying is essentially saying that applying both the transformation and its adjoint results in the identity matrix, simply scaled by the value of the determinant. Now, I know that all those matrix multiplications and determinants we just worked through in the example might seem a bit abstract. So, let's step away from the numbers for a moment and look at a real-world analogy to help you visualize what this theorem actually means. This concept of scaling is crucial because, as we will see in our next few slides, understanding this relationship is exactly what allows us to calculate the inverse of a matrix. Common mistakes. First, be very careful not to confuse the determinant of A with the matrix A itself. Remember, the determinant of A, which we write as the vertical bars around A, is just a single number, or a scalar. On the other hand, A is a full matrix. Because of this difference in nature, you cannot perform operations like subtraction between a scalar and a matrix. Always keep track of whether you are dealing with a single value or a grid of numbers. Second, a very frequent mistake is forgetting to include the identity matrix, I, in your final equation. You might be tempted to write that a multiplied by the adjoint of A equals the determinant of A. However, as we saw in our step-by-step example, the left side of the equation is a matrix, so the right side must also be a matrix. To keep the equation mathematically balanced, you must multiply the determinant of A by the identity matrix. This ensures that both sides of your equation are matrices of the same order. Finally, watch out for calculation errors. When finding the adjoint of A, it is easy to find the cofactor matrix and stop there. But remember, the adjoint is the transpose of that cofactor matrix. If you forget to transpose the matrix before performing the multiplication, your result will not yield the diagonal matrix we are looking for. Always double-check that you have swapped your rows and columns correctly. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. Even if you understand the theory, these small errors can lead to incorrect answers in your exams. Once you master these details, you'll be perfectly prepared for our final summary. Key takeaways. First, remember the core principle we've been working toward. The product of a square matrix A and its adjoint, A, is always a scalar multiple of the identity matrix. This means that when you multiply them, you don't just get any random matrix. You get a very specific, clean result where the diagonal elements are all the same. To put that into a formal mathematical statement, the formula is A times A, which is also equal to A times A, equals the determinant of A, denoted as absolute value of A, multiplied by the identity matrix, I. It is also important to note that this property is incredibly robust. It holds true for any square matrix, regardless of whether the matrix is singular, meaning its determinant is 0 or non-singular. The relationship remains consistent either way. Finally, I want you to realize why this matters so much. This relationship is actually the theoretical foundation used to derive the formula for the inverse of a matrix. If you look closely at the relationship we've proven, you can see how we arrive at the formula for an inverse, which is 1 over the determinant of A, all multiplied by the adjoint of A. This is the very tool you will use to find matrix inverses in our next lesson. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. Make sure you have practiced the steps in our example, and I will see you in the next class.